Hello, this is Captain Chaudhari. In my series of videos on basic ship stability calculations, today I'm going to do bilging. This is the bilging of a compartment that contains liquid. To be precise, it has a liquid of relative density 0.85. Here's the question. Let me draw the diagram first. Somewhere here you would have midships. So suppose this is forward, this is aft. It says the forward bulkhead is amidship, so I would draw the forward bulkhead here, and this is a compartment of length 14 meters. The box vessel floats at even keel draft of 8 meters, and there's liquid in this compartment of the height 9 meters and density 0.85. Sounding is 9 meters. The kg of the ship before damage is 6.4. So let us start doing the question. As I told you, constant displacement. We are going to do the question by constant displacement method only, but the requirement for doing a calculation, the initial requirement for doing a question by constant displacement method is that compartment to be damaged or compartment that would be damaged is void of liquid. So we need to get the kg and we need to get the draft while this liquid is out. So although this compartment gets damaged and then it settles to the new draft, the liquid goes out, we assume that the entire oil goes out and the place is filled up with the water, right? With the outside water, that is the seawater of density 1.025. We can also say that if this happens this way, the effect would be same if we had pumped out the oil somewhere else, and then the water gets filled. Then after the damage, the water gets filled up. The quantity of liquid or oil is 14 into 24 into 9, and I will multiply this with 0.85. 14 gives me 2570.4. 2570.4 tons. So much of oil is there. Let's find out the displacement of the craft. Displacement of the craft is 140 into 24 into 8 into 1.025. 140 into 24 into 8 into 1.025 gives me 27552. 27552. So as I said, we have to on paper, or we have to assume that the oil was pumped out. So after pumping out the oil, what would be the kg? Let's find out by kg by moments method. So we have weights in ton, and then we have kg in meters, and then we have vertical moment in kg meters. So the first weight is the displacement of the ship itself, 27552. Kg given in the question is 6.4, and then we remove 2570.4, and because the height is 9 meters, the kg of the liquid that is removed is 4.5 meters. So 27552 into 6.4 gives me 17632.8, and then 2570.4 into 4.5 gives me 1156, gives me 11566.8. So this is removed. So me 164766, and this is to be divided gives me 6.595 4981. So the constant displacement for the question is going to be 24981.6 tons. This displacement is not going to change, and the kg is going to be 6.595 meters. The quantity of oil in the compartment is 2570.4. Let's now find out the mean draft after the oil is pumped out. So we have displacement of the ship after the oil is pumped out as 24981.6 tons. Now length into breadth into new draft into 1.025, that is the density of medium outside, should be equal to 24981.6. So the new draft is going to be 24981.6 divided by 1.025 into 140 into 24, 7.254. So 7.254 is going to be the mean draft after the oil is pumped out. Now we need to find out what are the new forward and aft drafts. So with this new draft, can we find out the BM longitudinal? BM longitudinal is L square upon 12D. So that is equal to 140 into 140 divided by 12 into 7.254. That is 225.163. 225.163. So this is going to be the GML. This is going to be the BML. BML is equal to 225.163. BML plus KB minus KG should be equal to GML. So, and KB is going to be half of the new draft. The new draft is 7.254. Half of that is 3.627. So KB is equal to 3.627. So let's do it. 3.627 plus 225.163 equals minus kg. Kg is 6.595. 6.595. 222.195. 222.195. Now to find out the drafts, like what we have done here is we have removed a weight from here, and the weight was 2570.4, and can we say from the midships the distance is 7 meters. So the trimming moment that is caused by removing this weight is, we will say trimming moment caused is equal to 2570.4 multiplied by 7. So trimming moment that is caused divided by 100 MCTC. MCTC is W GML upon 100L. So that is equal to 2498.1.6 into GML 222.195 upon 100 into 140. 24 divided by 140 gives me 396.48. 396.48. 6.48. That is the MCTC. Now, trimming moment, that is cost divided by 100 MCTC, is equal to trim change. So trim change is going to be 2570.4 into 7 divided by 100 into 396.48. 9648 gives me 0.454. 0.454. So this is the trim change, and because the ship is not damaged, we would say TRA equal to TRF equal to TRC upon 2, because the change of draft due to change of trim forward and aft will be same. So half of this, 0.227, 0.227 is TRA as well as TRF. So the new draft that you have, that is 7.254. As you know, we have discharged the liquid from the after part, so after draft will reduce. So after draft will become 7.254 minus 0.227. 7.027, and the forward draft will become 7.254 plus 0.227, that is 7.481. So we have 4.5 draft as forward as 7.481 and aft as 7.027. So now that we have got the kg of empty ship means the compartment empty, and we have got the mean draft, we start from here a fresh calculation, that is damage to an empty compartment. So the initial conditions are, you have the draft forward 7.481 and aft 7.027. So we have a trim of 0.454 meters by head. Now the ship would be like this. Here is the compartment, and the starting condition is a forward draft is more than aft draft. Forward draft is 7.481, aft draft is 7.027, and we need to find out the draft at this point, because this empty compartment, when it gets damaged, the loss points is to be considered by the height at the mid-length of the compartment. Let's find out the height at mid-length. This distance is 63 meters, because from midship to aft is 70 meters. So this distance is 63 meters. Let us find out what is the correction for 63 meters. Now the draft change for 140 meters is 0.454. So the trim correction or the draft correction for 63 meters would be 0.454 divided by 140 multiplied by 63. So 63 into 0.454 equals divided by 140 gives me 0.204. So the draft at this point is going to be 7.027, that is the aft draft, plus 0.204. So that is 7.231. So the loss buoyancy is going to be the length of the compartment, that is 14 meters, breadth of the compartment, that is 24 meters, multiplied by 7.231 gives me the loss buoyancy as 2429.6 1.616 meter cube. An intact water plane area can be considered as total, that is 140 into 24, minus lost, that is 14 into 24. So that would be 140, that is 3024 meter cube. So sinkage is going to be lost buoyancy upon intact water plane area. So that is 2429.616 divided by 3024. So 2429.616 divided by 3024 gives me 0.803. So as you can see, there is some amount of approximation being done in the calculation, but we more or less get an idea like what happens to the ship. So here we've got the sinkage as 0.803. Now one of the first things that is done in an intermediate or end compartment bilging, as I discussed earlier, is to find out the FF1. And to find out FF1, we take the moment of area about the midships. Okay, now looking at the plan view, we have the damage here, and we had said that in FF1 the first thing we do is A into 0. We take the moment of the entire area about own midship, so the distance is 0, minus 14 into 24 into 7, because the distance from here to here is 7, divided by intact water plane area. Now intact water plane area is 126 into 24. We had seen this. Total area minus lost area. There is no permeability. So 14 into 24 into 7 equals, divided by 126 into 24 gives me 0.777. So as we know, the damage is over here. Initial center of flotation was here. It is going to shift in opposite direction to F1. FF1 is equal to 0.777 meters. Now looking at, now this means that with this new water plane area, the first thing that would happen is the ship is going to sink bodily, and thereafter, because the damage is rather in aft part, the aft will get submerged, so the draft over here will increase, right? But the center of flotation would shift in opposite direction, so this is the new F1. Now to find out the shift of center of buoyancy, like initially the center of buoyancy was here, afterwards the center of buoyancy is going to shift in an opposite direction, right? So let us find out how much is the BB1. What we can do is we can take the moment about aft of underwater volume. So entire underwater volume, we take the moment about aft. So the new mean draft is 7.254 plus 0.803. 8.057. Let us find out what is the shift of center of buoyancy. To find out BB1, let us find out LCB1. Now to find out the new LCB, this is aft, this is forward. Let us take the moment about aft. First, the total underwater volume. Total underwater volume is 140 into 24 into 8.057 multiplied by, this is the underwater volume, multiplied by 70. So the mean draft over here is 7.231 before damage, and after damage the draft becomes 7.231 plus 0.803. So we assume that initially the ship sinks bodily, and thereafter the trim change will take place. So this is 8.034. So from this underwater volume, we remove the underwater volume of this part, which is either lost or wasted. So this underwater volume from the compartment is 14 into 24 into 8.034, and this is to be divided by intact underwater volume, that is 140 into 24 into 7.254. So we have taken the moment of the whole underwater volume up to mean draft 8.057. That would be multiplied by 70, but we need to remove this lost or wasted underwater volume from the compartment, and the distance is 63 meters. Divide by intact underwater volume, which has to be taken till the draft of 7.254, not the initial draft. So let's do the calculation. 140 into 24 into 8.057 into 140 into 24 into 8 gives me 70.771. Gives me 70.771. This means that the center of buoyancy, which was 70 meters from the aft, now it is 70.771 meters from aft. This means that BB1 is equal to 0.771. So I'll write it here. The BB1, that is the shift of center of buoyancy, is 0.771. So mind you, the shift of center of flotation is 0.777 and shift of center of buoyancy is 0.771. This is giving slight allowance to the trim of the vessel, and it says that, it implies that the shift of center of buoyancy is slightly less than shift of center of flotation. If it was even keel condition, I would have said the shift of center of buoyancy would be equal to shift of center of flotation. As I told you, some amount of approximation is there in the calculation, but we will generally get an idea like what happens in constant displacement method, taking certain approximations into account. So next we want to find out how the vessel will trim, and I have told you before that trim change upon LBP is equal to BB1 upon GML, right? So to find out the GML, we need to find out what is the BML, and to find out the BML, we know that the vessel will have a residual moment of inertia about an athwartship axis passing through the center of flotation, and from that residual moment of inertia we need to divide intact underwater volume, which is 140 into 24 into 7.254. So let's find out the BML now, right? So first we need to find out what is the total moment of inertia regardless of damage, not considering the damage, about this axis. So that would be 24 into 140 cube upon 12 plus 24 into 140 into 0.777 square. From that I need to remove 24 into 14 cube divided by 12 plus 24 into 14 into 7.777 square. This whole thing is to be divided by intact underwater volume. Now in this calculation, 24 into 140 cube, that is BL cube upon 12, gives you the moment of inertia of total waterplane about this axis. But we don't want this axis because FS shifted here, still assuming that there is no damage, undamaged waterplane area. What is the moment of inertia? So that is BL cube upon 12 plus 24 into 140 into 0.777 whole square. That is, we have shifted the moment of inertia from here to here by theorem of parallel axis. So we added AD square. But that is the total moment of inertia of water plane area, assuming that there is no damage. But there is damage, and this damage about own axis is 24 into 14 cube upon 12. That is damage about own axis. But if we shift this damage to this axis, the distance to shift is, this is 7 meters and this is 0.777. So total distance to shift is 7.777. So we have the loss about own axis as 24 into 14 cube by 12. Loss about the remote axis is, we add plus AD square. A is 24 into 14, D is 7.777 square. D is 7.777. So AD square we add, so that we know that total loss about the remote axis is so much. So when we solve this expression, it becomes 54, the numerator becomes 549,028.5 minus 25809.8. Right? That divided by intact underwater volume. Intact underwater volume is to be considered not for 8 meters, it is to be considered for 7.254 meters. So divide by 140 into 24 into 7.254 gives me 224.187. So 224.187 is the BML. So let's do the remaining part of the calculation. First of all, let us find out what was the KB. 7.254 was the draft before damage, and then there was the sinkage of 0.803 meters. 8.057. So KB after the damage, I would say 8.057 divided by 2, that is 4.02, 4.028. So this is KB. Now BML is 224.187. So KML will be 228.215, and from this I remove the kg. Not the kg that is given in the question, but kg after pumping out of the oil, that is 6.595. $221.620 will be the GML. Now we have trim change upon LBP is equal to BB1 upon GML. So therefore trim change will be equal to BB1. BB1 is 0.771 into LBP 140 divided by GML, that is 221.620, gives me 0.487. Now as you know that the center of flotation has shifted in the forward direction, and that has increased the LCF, and new LCF is 70.777. 70.777. So if we have to find out TRA, TRA is equal to trim change into LCF upon LBP. So that is 0.487 into LCF 70.777. That is 0.246. And this, when I subtract from 0.487, gives me TRF 0.241 meters. So let us find out what is the final draft now. So we will do the standard trim format calculation. We had the initial draft forward as 7.481 and aft as 7.027. There was a bodily sinkage of 0.803, and then As you can see, the damage is in the after part, and if the damage is in the after part, the TRA will be positive, so I will put plus 0.246, and if TRA is positive, TRF has to be negative, so it is minus 0.241. So let's find out the half draft first. 7.027 plus 0.803 plus 0.246 gives me 8.076 meters. And let's find out the forward draft. 7.481 plus 0.803 equals minus 0.241. It gives me 8.043. So the calculation is slightly complex, and that is because there was a liquid in this compartment, and when there's liquid in the compartment, we need to do the calculations in two stages. First stage, we remove the liquid, find out the new mean draft, find out the new draft at the damaged compartment is important. Apart from that, we find out the kg with the liquid out from the compartment, and then we damage the compartment. And because it is now damaged to an empty compartment, we can do the calculation by constant displacement method. But in the constant displacement method, there are two very important things. One, kg does not change, and second thing is the intact underwater volume is to be considered with the underwater volume without the liquid in the compartment.